Okay, for the second example in our application section, we're going to talk about maybe throwing a ball, shooting something up in the sky, something we call projectile motion. And there's a couple different things that we need to be aware of. One is some notation thing. V sub 0 is our initial speed or our initial velocity. And then S sub 0 is our initial height. And why we pick S for that instead of H, I don't know. It's just what our textbook uses. There are certainly some places, maybe in calculus, where we use S instead of H. Just something we have to kind of live with. And then I want you to remember that you've probably seen this sort of formula right here before. Maybe you didn't realize that it was V sub 0 and S sub 0 that were there. You may have been given numbers already. But there have been problems that you've looked at in the past where you basically threw something straight up and straight down, and you would use this formula and find different heights at various times. What we're going to be using are formulas right here, and that represents where we're not just moving straight up and down, we're moving at an angle. And so I just want to compare what we have for y, for the heights. It's very, very similar to what we had up here. The only difference is in this middle part, this middle term, we now have a sine of theta. And then we have something now for x, which is totally new. It's the initial speed times cosine of that angle that we're moving at the beginning of the problem times time, and that gives us our two parametric equations. Now I want you to think about this. When we go straight up and down, our angle from the horizontal is 90 degrees. Cosine of 90 is 0. And so all of this would go away when we're in that one situation of 90 degrees. Sine of 90 on this side is 1, and so in this case sine of 90 doesn't matter, it just goes away. And so this equation that maybe you've used in the past is really just a special case of the ones that we're going to be using today. So that's a lot of talking there, just kind of discussing where this comes from. Now let's go ahead and plug stuff into the formula in a different application problem. So our problem says Kevin hits a baseball from 3 feet above the ground, has an initial speed of 100 feet per second, and has an angle of 18 degrees with the horizontal. The question is, will the ball clear a 20-foot wall that is 400 feet away? So we want to come up with some equations for this. For our x equation, we would get our initial velocity of 150 times cosine of our angle, cosine of 18, times time. And for y, we would have negative 16 t squared plus our initial velocity of 150 times sine of our angle measure, so sine of 18 times t. And now notice I closed the parenthesis on both of those because I want to make sure just the 18 I'm taking sine of. And then our initial height for this was 3, so plus 3. Okay, those are the two equations that we would be using. So I'm now going to go to my calculator and type those in. Let me clear this away a second. Make sure you have it written down. Okay, I'm just going to go ahead and type that in. So I would have, let's see here, 150 times cosine of 18, close the parenthesis, times t. And then for y, I have negative 16 t squared plus 150 sine of 18, close the parenthesis, times a t, plus 3. Okay, so we just got to kind of make sure we have everything entered in correctly. One thing I want to quickly check is my mode. Now I'm in radian mode right now, and because my angle was in degrees, I want to make sure that I select degrees. Everything else looks like it's okay. So go back to y equals. Maybe we talk about window settings a second. time, it's not going to take that long for this baseball to travel. So I might just go to 4 seconds now. I'm still going to keep it at 0.1 for my T-step. My X min and X max, that's how far the ball is going. So I think going to 500 feet makes sense since our wall is at 400. And then for our Y max, how high do I think the ball will go? Maybe I'll put in 50 feet for now. Okay, so I'm just going to graph it, see what happens. Oh, got an error. Let's see here. What is my mistake? And I probably used the wrong negative symbol, so let's go ahead and do it on the keyboard here, negative. Okay, now we'll graph. Okay, so we have what looks like the path that this baseball would take as it travels. I want to see what's going to happen at, will this baseball clear the wall at 400 feet? So one way I could do this is to trace. And I'm just going to go until X is close to 400, as close as I can make it. Notice the T values are just going up by 0.1 every time. Okay, so we're getting close. Well, you can already tell. Okay, so we're pretty close to 400 feet for X, and my height is only 7 feet above the wall, so the answer is going to be no. If you do want kind of a nice, easy way of making the wall, this is something that you could try to do. I want X, I'm going to enter in a second parametric equation, and I'm going to have X equal 400, because that's where the wall is. I always want it to be 400. And then I'm going to make Y, basically I'm going to build up a lot of points right above it. So I'm going to see what happens if I want my wall to be 20. I'm going to divide by whatever my T-max is. So if I go back to my window, my T-max was 4. So it kind of changes based on what I'm trying to do here. But T-max is 4, and then times the T. So I'm going to enter that into Y equals a second. Okay, so 400, and this would be 20 divided by 4 times T. Okay, and if I graph it again, I should see a wall appear. Okay, and there was the wall right there. So it would have to be above this if it was going to work. So just something kind of interesting. Don't necessarily have to do that. But okay, I'm going to simplify that. We're going to erase this. Okay, and our answer is no. It's only, I think it was about 7.34 feet tall at 400 feet away from the plate. Okay, we'll stop this video and go from there.